In today's lab, we will be using a mini launcher to calculate velocity using different angles. Once we determine our position and time, we can solve for our muzzle velocity. In this experiment development, we will test the launcher of different angles compared to our theoretical and finalize our percent error.
And then for our materials, it's the steel launcher, the steel ball, the tape, the carbon, that carbon paper, and then the ruler.
Like about right here, I think. We can tape the paper and do it.
Okay.
Why is this fun? I feel like that one was short. That was 3?
Yes.
Okay. Yes.
Did it hit? Yeah, it did.
Did that one hit? I don't think it did.
That one. Okay. That one did.
Okay. It's like on the edge.
Hi guys, welcome. So this is lab report 6. We are team number 3. For our lab number 6, it was the experiment using the launcher. I'm just gonna go ahead and demonstrate what we were using here. So here's the launcher right here. As I explained earlier in the video, we had a metal weight, a protractor, a launch point, a range setting, and a lanyard. So this was basically like our equipment setup that we explained earlier in our materials. So first, we're gonna come down here to our first table, which is gonna do our calculating for our muzzle velocity. So here we went ahead and found the points in our experiment prior to experimentation, and it went ahead and gave us all these points. So our initial position, which was 0 meters per second, our Y initial position, which was 0.904 meters. Sorry, did I say meters per second? 0 meters. Final position, which ended up being 1.387 meters. Our Y final, which ended up being 0 because the ball at the very end would be at ground level. Our initial velocity for X, which would be which we found was 3.233 meters per second squared. And then our V final for our Y, our velocity for our Y value was 0 at the end, because it wouldn't be moving towards the X coordinate anymore. It would just be moving horizontally. And then same thing, our acceleration for the X coordinate would be 0 meters per second. And then for our Y coordinate, it would just be what gravity is. So we headed in and found these values, or we found our time. We found our time using this formula right here, which is basically our initial y position divided by our gravity. So then once we use that, we went ahead and found our time, which is going to be right here. It's 0.429 seconds. And with that, it's here actually. Excuse me. So then this is the values that we input here, and then we got this value right here. And with that value, we went ahead and used this second equation, which is just basically going to give us our muzzle velocity. So here, I went ahead and wrote it down for us. So it's going to be x final over time. And then that would just be this value right here, which we put into here and ended up giving us our VM, or which is also our Vx as well. So Vx would be 3.233 meters per second. And so then afterwards, we went ahead and started to do our experiment. We would have this table right here. And just for time's sake, I went ahead and didn't have the equations here, but the values I will be explaining through here. So basically, first off, we went ahead and did our theoretical distance. So we basically just determined our theoretical prior to doing all these values. Okay, so with this graph, we would be able to, with these equations, we were able to determine our theoretical position. So basically in these, we would just sub the value of theta, and we would want to go ahead and put these angles here. So first we would input those angles, and then they would give us our Vx and our Vy value. And then afterwards, we would then use our calculating our time of flight, which is going to be step 3 here. So we would just input these values, A being obviously gravity, so half of gravity, and then our Vy would just be our velocity in the y component, and then our C value would just be our y initial. So then after inputting these, we would put it into our time slot, and then after we figured that value out, we would then put this value and combine it with our VM. After figuring that out, we would plug it in with our VM, which, as we determined already in the prior page, it was going to go ahead and be 3.233 meters per second. So after that, we went ahead and input those values and then multiply times the cosine of the angle, which theoretically would be these 3 right here. So then afterwards, we went ahead and did that for 30 degrees and then multiplied it times our time, which we got from this value. And then afterwards, it would give us a theoretical distance of 0.827 meters. And then afterwards, as you saw in our experiment here, I actually have the experiment right here. So these are all of our plots. We're just going to be focusing on the 30 degrees at the moment. So after we did our experiment, this was the 30 degrees that we got. These were the 5 points that we were able to determine. And then we just found the distance. We found the distance between all of them. We found the distance between the 5 points and then went ahead and put it in, went ahead and found the average of these 5 points, which is basically this image right here. So we found that we added all the points together and then we divided them by 5 to find our XF, which would be our experimental distance. And then afterwards, we went ahead and just used this equation right here, our percent error, and that would went ahead and give us a value of 5.4. And then afterwards, we just repeated the process of using our 45-degree angle, which gave us 2.609 meters, and then our experimental distance, which I'm just going to demonstrate here. So that one would be this one right here. So then we used it for a 45-degree angle, basically repeated the same process with this image right here, and that went ahead and gave us a percent error of 3.6%. And then same thing again for the final time. We went ahead and did our 60 degrees, which gave us a theoretical distance of 1.289 meters. And then, like I said, same thing. Now we have it in the 60 degrees, which actually came up shorter than these in comparison with the shooter mechanism, but this would be the distance from the line as shown here. So basically same thing, just got the mean of the entire process or the experiment, and then got a value of 1.16 meters, compared those two values together, which gave us a percent error of 8.9%. And yeah, so afterwards, after determining that, we went ahead and answered our conclusion or our reflecting questions, which I have the answers here, but I'm just gonna go ahead and repeat the question and then tell you the answers that we have. So first question is, where do we think our percent errors come from? Me and my team determined that we most likely get the percent errors from, which is the most reoccurring thing, is most likely human error, something on our part, whether it was the capstone or just us, maybe not setting it up correctly, but yeah, just having like small faulties. And now we're gonna have like a combination of a question. So 2 says, do you think there are factors affecting our experiment that are not considered in the formula we are using, and which ones? So me and my team said yes, that there are factors that affect our experiment that we don't consider in the formula. Obviously, we want it to be negligible since we are barely starting out in physics, so this is physics 1. But the factors that would be most significant would be most likely friction and air resistance with the balls, and when they touch the paper, and just like the distance. That's why all the distances are different from all these values right here, which most likely play a factor with air resistance and friction. They don't play the entire role, but these are factors that do contribute to that. And then we are asked for question number 4, are they significant? Me and my team said they are significant because almost every experiment, or a lot of the experiments, have to deal with things such as gravity, friction, air resistance, the normal force, just dealing with forces in general. So yeah, it is a pretty significant, or they are pretty significant when considering an experiment and creating a formula. So yeah. Then the next question says, do we think there's a way to minimize it? We said that it's hard to say, although if we have a manipulated environment such as a frictionless surface, or like a way to get rid of air resistance. So it is possible to minimize it, but it would also have to be a very controlled area to do so. And then for number 6, we said, are all our percent errors equal? Why or why not? We said no, which is shown here. All our percent errors are roughly different. And we said because each of them may have a different level or degree affecting them, such as environmental factors or human error, or the different degrees that they're being shot from the system. So there are different levels or degrees of things affecting them, and sometimes they happen simultaneously. So it's hard to say that they're going to end up being the same, theoretically speaking, but it's very much possible. It was just not in this case. They did not equal to each other. So yeah. And then to our conclusion here, we said to conclude, the experiment was fairly simple, yet required a multitude of trials, which is just like trial and error, trying to get it to land on the paper itself. Afterwards, after we figured a good angle, distance, whatnot, it was fairly simple to complete the graph for each angle with little percent error, as shown here, and with the helpfulness of our graphs and our equations, we were able to determine so. And yeah, so basically here are our credits here. Alex, which is me, did the setup and the calculations for the experiment. Sophia went around and helped out with our recording and our materials. Sherilyn went ahead and helped out with recording in our experiment. Nadine went ahead and helped with recording and doing our introduction part. And Ileana went ahead and helped with experiment and calculations. Yeah, thank you guys.